Hello, everyone. This is Dr. Lennon. So we're going to look at 1D today. So analyzing arguments. Some of this overlaps with some of the conditional statement truth tables we looked at. But basically, we're breaking everything down into two types of arguments: inductive arguments versus deductive arguments. So an inductive argument starts with specific premises and tries to make a statement about a more general conclusion. For most of these things, you're not able to actually prove them true, but you can only talk about whether or not it's a strong argument based on how sound the premises are. There's another type that you can talk about in mathematical proofs with formulas, but we're not going to be looking at anything that's specific in this section. The other type, deductive, are the more common ones we see. Oh, here's an example. So bluebirds fly, hummingbirds fly, cardinals fly, all birds fly. Okay, so in general, most birds fly, but we know that the statement, although it seems like a strong argument because you can point to a very large proportion of the birds and almost all of them fly, we do know examples of birds that don't fly, like ostriches, penguins, turkeys, things like that. So, although this is in some sense a strong argument and the conclusion is generally true, it's not completely true. Deductive is when you have general premises that reach a more specific conclusion. So these types of arguments we tend to use more often when we can determine whether or not they're true. So premise, all doctors are intelligent. If all doctors are intelligent, then you can point to a specific doctor, and then he will therefore also be intelligent. So all doctors are intelligent. There's a specific doctor, Dr. Jones. He's a doctor, therefore he's intelligent. So again, as I stated before, an inductive argument doesn't prove its conclusion true, so it's evaluated based on its strength. So an argument is strong if a compelling case is made for its conclusion. Again, there's a little bit of subjectivity to strength in this setting when we're talking about just reading sentences and trying to understand their underlying logic. And again, an argument's weak if it's not well supported by its premises. People try to make arguments like this fairly often, so it's good to try to get an understanding of when their premises are not so good or not that well related to the general conclusion that they're attempting to make. Okay, so let's look at this example. A movie director tells her producer, who pays for the movie, not to worry, the film will be a hit. As evidence, she cites the following facts. She's hired big stars for lead roles. She has a great advertising campaign planned, and it's a sequel to her last movie. Explain why this argument is inductive. Well, it's inductive because she has three specific premises she's looking at. There's big stars, the advertising campaign's good, and it's a sequel to a hit movie. So those are three specific things. And it's trying to say that more generally her film will be a hit because of that. So, of course, this would be considered a somewhat weak argument because there are many movies that were not successful that have all three of these specifics as a premise, but it didn't necessarily lead to the movie being a hit. So there are many, many, many sequels of movies with big stars that didn't end up being hits. And advertising campaigns, so forth. But, if you were really trying to use that and say it was a strong argument, you'd probably want to have some more specific data to show the strength of those three specific premises meriting the more general response. Like if you could say something like, well, out of the last 10 years, if you would check these three boxes, so and so many movies went on to be profitable in such a way. But this is just kind of pointing to three things and saying, okay, well, those three things prove it. Not necessarily. So the solution, each of the three pieces is specific, as we talked about, but the conclusion is more general, so that makes the argument inductive. But the argument is weak because even the best planned movie can flop. Okay, so it's basically essentially what we said. All right. evaluating deductive arguments. So apply 2 criteria to evaluate a deductive argument. Again, remember, for the deductive, we're looking at something general, and we're saying something, making a statement about something, a consequent that is more specific. So the argument's valid if its conclusion follows necessarily from the premises, regardless of the truth of the premises or conclusion. Okay? So if your premise is false, you can still technically have something that's a... if you remember back to the truth tables from the A implies B or P implies Q, we saw that P implies Q was true in every case except for when we had something false trying to, something true trying to imply something false. So 3 of the 4 cases we actually did get P implies Q being true. So the statement here is the argument is valid if the conclusion follows necessarily from the premises, regardless of the truth of the premises. Okay? But the argument is sound if it's valid and its premises are true. So a lot of times if you're making a statement and the logic is sound but the premise is false, it's not very interesting to talk about. I'm trying to think of a quick example off the top of my head. Let's see. Well, if we said something false, like so I mean, here's something that's it sounds kind of silly, but you could say the premise, the argument. I was trying to say something silly like the sky is orange. Okay, so that's a general thing. It's certainly not true because typically the sky is blue. And then if you try to say something more specific based on that, you could say the sky is the same color as oranges. You'd end up with something that's true based on the logic of it, but it's not sound because the premise is false. I don't know. It's kind of a silly, bad example just off the top of my head, but hopefully they'll have some examples for us to look at as well. Okay, so this is just a chart summarizing basically the differences and similarities between inductive and deductive statements. Again, inductive, we have general hypotheses, and we have... the conclusion is general, and the hypothesis is... the premise is specific. Whereas with deductive, we have a general premise that's pointing to a specific conclusion. Again, the inductive arguments, we're not going to be able to prove that they're true or say that they're true, but we can evaluate them in terms of their strength, so we could say it's a strong argument or a weak argument. Whereas with deductive arguments, we can talk about validity and soundness. So validity means the conclusion follows from its premises, but it's sound if and only if we're talking about a premise that happens to be true. And again, an inductive argument cannot prove its conclusion. At best, it can show the conclusion probably is true. Valid concerns only the structure of the argument. A deductive argument can be valid even when its conclusion is blatantly false. So again, we need, for it to be sound, we need the premise to also be true. The silly statements come about when you have a false premise implying something else, because the logical structure can still be valid even though it would not necessarily be sound. So testing validity, sometimes you can do this with Venn diagrams. Typically, I don't use Venn diagrams in this way, but and you'll see with the inductive argument, it looks kind of silly, but let's see what the example is. So draw a Venn diagram that represents all the information contained in the premises, and then check to see whether the Venn diagram affirms the conclusion. If it does, then the argument is valid. Otherwise, the argument is not valid. So sometimes we can see, like, for a deductive argument, the conclusion bubble being smaller than the premise bubble. And in that case, it's going to make sense because we're taking a general thing and implying something about something more specific. Whereas it gets a little bit fuzzier when we start talking about the inductive arguments. So evaluate the validity and soundness of the following argument. All fish live in water. So we can look at that statement on its own. All fish live in water. So we have the fish completely living in the things that live in water. And then if you look at kind of like the beige outside, I'm assuming that's just representing all animals. So the animals that do not live in water would be in the beige area outside of the blue bubble. So what do we say? The premise, all fish live in the water, tells us to draw the fish circle as a subset of the things that live in the water. All right, so whales are not fish. So whales exist somewhere outside the fish bubble, but if we didn't know anything about whales, we wouldn't know necessarily whether they live in the beige, in the blue, or somewhere in between. So whales are not fish tells us to put an X for whales outside the fish circle, but again, it doesn't tell us whether or not fish actually live in the water or do not live in the water. So for that reason, the X is drawn on the circle. And so the conclusion is that whales do not live in water. So this is not valid because based on how we've drawn everything, we don't actually know. I mean, I know we all know that whales live in water, but based on the Venn diagram and the way that the statements are laid out, we don't have a valid argument for that. So, the conclusion, whales do not live in the water, would require X outside the things that live in water, but the X from the premises is on the border, which means the premises do not automatically support the conclusion. So the first two statements together do not necessarily tell us that whales do not live in water. We would need something else. All right. Again, this may be a little bit clunky, and if you're thinking, well, I know where whales live, the question is not if you know where whales live. It's based on, does the fact that the first two statements together imply that whales do not live in the water, which in this case it does not. Okay, so the basic forms of conditional deductive arguments, basically we're talking about whether or not they're valid. So the two that are valid are the first and then the last. So if P is true, then Q, and Q is true, this is a valid argument structure. If P, then Q, where if P is not true, if Q is not true, then P is not true. This is also valid. This is an example essentially of the contrapositive. But the problem here is, again, this is not going to be an example of a sound argument because your premise P is not true. So if you have something false, you can imply something that's not true. And then the other two examples, if P is not true and Q is true, that's not a valid conclusion. And then if P is not true and it's implying Q is not true, again, this is not a valid conditional argument as well. So the main one here is the affirming the hypothesis, but denying the conclusion is also valid, but not necessarily sound. And they have all these names for them. I don't necessarily remember all the names, like affirming the hypothesis, affirming the conclusion, denying the hypothesis, or denying the conclusion. You can look that up if you have to. It's more important to just remember what to look for in terms of an argument being valid or not valid. Or invalid, I suppose I should say. Okay, so affirming the hypothesis, if we go back, what are they talking about? They're talking about this example right here. If P, then Q, or P is true, and then that implies Q is true. So, going back, let's consider the argument. If a person lives in Chicago, then the person likes windy days. Carlos lives in Chicago, therefore Carlos likes windy days. So, if we have the Venn diagram that we were trying to do with the whale thing previously, we have the people that like windy days. We have the people that live in Chicago under the windy days, according to that argument. So we have the Venn diagram with the P statement, lives in Chicago, lying completely in the Q statement. So nothing too difficult there. What does the second premise say? It says that P is true for Carlos. We therefore draw an X to represent Carlos and place it inside the circle, right? He lives in Chicago. Since he lives in Chicago, he's also in this bigger bubble saying he likes windy days, so that should be a valid argument. So use the Venn diagram to show that the argument is valid. That's what we basically just said. The conclusion states it's true for Carlos. He likes windy days, which he certainly does because he's inside that bubble, the blue bubble. So the X indeed is in the Q circle, so it's valid. So, yep, nothing too crazy there. Again, I typically don't always think about these things in terms of Venn diagrams. Usually I think of Venn diagrams as interactions between sets, but you can also do it with propositions or premises and conclusions here. Okay, affirming the conclusion. So I think this is one of the examples of an invalid argument. So again, they're going to try and do it with the Venn diagram test. So premise, if an employee is regularly late, then the employee will be fired. That tells you a reason. If somebody's regularly late, then they will be fired. But certainly you can be fired for other reasons. So you can kind of already see why this argument's not going to be valid if you look at the premise. Sharon was fired, therefore Sharon was regularly late. That's not necessarily the case, right? There's lots of other reasons you could be fired for. She could have been stealing from the company, but always been on time. But let's do this now with the Venn diagram bubbles. Again, we're going to do the Venn diagram. We have the two premises and the conclusion. So again, we have the people that are fired, and the people that are regularly late are only a small portion of that. And they drew the X for Sharon on the border because she was fired, so it's certainly possible she was fired for being late, but she could have been fired for a different reason altogether. So we don't know whether that red X is inside the regularly late bubble or outside the regularly late bubble and inside the fired bubble. So we see that we don't know, so this argument is invalid. Yeah, so that's the explanation here. The second premise asserts Q is true for a person named Sharon. The premise doesn't tell whether she was regularly late, so that's why they placed it on the border, as we said. So, so the diagram should have the X inside the late bubble. It doesn't. It's on the border, as we mentioned. So the argument is invalid for those reasons. And again, you probably could have thought that one through without necessarily appealing to Venn diagrams, but we can do it that way as well if you're more visual, and that tends to help organize the information. Okay, so another one. We've got probably two more examples to do. If you like the book, then you'll love the movie. You did not like the book, therefore you will not love the movie. Again, you can see why this might not be true. So for example, I think this makes sense. There's plenty of movies that people like that were based on books where they didn't read the book, so you don't know whether they liked the book or not. Anyhow, let's look at the diagram. So if we do it, basically we've got the people that like the book and people that either didn't read the book or did not like it. And then we've got the people that are involved with the movie. So, are we not using a Venn diagram for this one? Oh, no, we are. So, okay, sorry. So, the second premise asserts that P is false for you, so we put an X outside the P circle. Yeah, so we're going to see the Venn diagram here in a second, and then we'll think in terms of that. So, again, we have the people that love the movie, then we have the people that like the book. But in terms of the people that show that P is false for you. Okay, so let me step back so we can look at the logic one more time. I'm kind of forgetting because the conclusion is you will not love the movie. So you did not like the book, therefore you will not love the movie. So again, the conclusion is that you do not love the movie, but not liking the book doesn't necessarily place it outside the blue circle. You could not like the book, which would be outside the P bubble, but you could still like the movie. So we've placed the X on the border now. It could be in the beige region and the blue region. The only region it wouldn't necessarily be in is the like the book bubble. So you could not like the book, and you could certainly still love the movie, or you could not like the movie based on this picture. So that shows that this argument, again, is invalid. Use a Venn diagram to test the validity of the following statement. premise. So denying the conclusion, this is the last one where typically one of the premises is false, so we get a valid argument, but maybe it's not necessarily sound. So first premise, a narcotic is habit forming. Second premise, aspirin is not habit forming. And then the third, aspirin is not a narcotic. Okay, so we see what's going on here. Again, with the Venn diagrams. Let's see what they say. They start by rephrasing the first premise in the standard conditional form by writing it, if a substance is a narcotic, then it is habit forming. Okay. We identify P, a substance is a narcotic, and Q, the substance is habit forming. So that's what we're going to draw in the Venn diagram. And then the second premise asserts that Q is false for aspirin. It's not habit forming. Therefore, we place an X representing aspirin outside the Q circle. The conclusion states that P is false for aspirin. It's not a narcotic, which means that X representing aspirin should be outside the narcotic circle, and it is. So we get a valid argument as well. So we've got all the habit-forming things Q, and then since we know narcotics are habit-forming from statement P, we put it there. And then since aspirin is not habit-forming, it's outside the habit-forming bubble, which means it could never be in the narcotic bubble. So we get a valid argument for that reason. So again, we have a valid argument in the fourth case of the types of conditionals that we looked at. Deductive arguments with a chain of conditionals. So another common type of deductive argument involves a chain of 3 or more conditionals. Such arguments have the following form. Premise, if P then Q. Premise, if Q then R. Conclusion, if P then R. So if a particular change of conditionals is valid, if P implies Q and Q implies R, it must be true that P implies R. So if you can form that logically, that chain, then we can make kind of a stronger statement by skipping that middle step. Determine the validity of this argument. If elected to the school board, Maria Lopez will force the school district to raise academic standards, which will benefit my children's education. Therefore, my children will benefit if Maria Lopez is elected. So that's certainly going to make sense if the statement is true. So it can be rephrased as a chain of conditionals. If Maria Lopez is elected to the school board, the school district will raise academic standards. If the school raises academic standards, then my child would benefit. If Maria Lopez is elected to the school board, then my children will benefit. So the conclusion, when you remove everything, you kind of miss out on the why, but the same logic certainly holds. So yeah, so statement P says Maria is elected to school board. Q, the district will raise academic standards. R, my children would benefit. So yeah, the argument's valid. If you just state it in the conclusive form without the academic standards, you might not see why. So that's why it's maybe more interesting to see the chain of conditionals. But yeah, we still have the valid argument based on the chain of P implying R, or P implying Q and then Q implying R. Hence, P implies R. So we were just basically rewriting the sentences, cutting out the Q statement. Okay, so perhaps more than any other subject, mathematics relies on the idea of proof. A mathematical proof is a deductive argument that demonstrates the truth of a certain claim or theorem. They use lots of words for certain things. Some of them have meanings like, sometimes you might see something written as a proposition. A theorem is kind of like a bigger thing. Sometimes a lemma is a statement about a mathematical statement used to kind of prove something more important. So sometimes lemmas are used to prove theorems, but basically all of them are just claims that we try to prove with a bunch of mathematical statements. So a theorem is considered proven if it's supported by a valid and sound proof. Although mathematical proofs use deduction, theorems are often discovered by induction. Yeah, often the way we figure things out, sometimes we write them backwards. That is certainly true. So we'll look at a very basic one. Test the following rules for all numbers. A times B equals B times A. This is inductively testing, so this is not going to prove that this is actually true. It's just going to look at a bunch of examples, right? Is it true for 7 times 6 equals 6 times 7? Sure, they're both 42. If we do it with these two numbers, is it true? So you can punch all these in the calculator and see that they exactly come out. But you're just testing. A lot of times in computer science and stuff like that, they'll do that. They'll run a bunch of examples to see if anything looks like it's going off, but it's not giving a full proof. It's just saying it's working for a ton of examples. To prove it, you have to do so using a bunch of mathematical statements based on simple claims that we know that are true. So sometimes those are known as axioms, and we use axioms, and then we use these statements, and we say why they're valid. And we know it's true in all cases, not maybe just in a few. So the 3 cases are somewhat different. They've got fractions in an example, decimals in an example, negative numbers, and the rule works in all 3 cases. So this is a strong inductive argument, but it's not proving the rule. So it gives you reason to think that it's true, but it's not necessarily a proof. All right, so that's it in this section. So we've gotten a lot of examples. Looking at inductive and deductive statements. For the deductive ones, which are probably going to be the most important ones, we looked at what it means for them to be valid and sound, and then we also saw some ways to test their validity using Venn diagrams. So this is Dr. London signing off.